So now let's talk a little bit about internal energy and what that represents. So now we're going to get really specific within the molecules and within the reaction. So when we talk about all the different kinds of possible energy in a substance, we call that internal energy. Give that the symbol U. And so that internal energy is going to be made up of both kinetic and potential energy that's inside the molecule or molecules. So kinetic energy would be the movement, of course, so the molecules are moving. And then the potential energy inside a molecule has to do with bonding, stored energy within bonds, attractions between molecules, things like that. So we've already talked about the first law of thermodynamics and how it, so in this case, when we're talking about a reaction, the first law of thermodynamics relates to the changes in internal energy of the system. So either energy that flows in or out of the container. It turns out, and we said this earlier, it turns out that there's actually two kinds of energy transfers that we're really going to focus on. Heat, which we've already talked about, and work. Work is sort of the other one. And all the internal energy is made up of these two kinds of energy, heat and work. So let's talk a little bit about what is work. Work is defined as the energy transfer into or out of a thermodynamic system whose effect, I'm just going to read it to you, whose effect on the surroundings is equivalent to moving an object through a field of force. So an example of this. So we've already done a lab where we've reacted zinc and hydrochloric acid, and we know that hydrogen gas is formed. So if we think about, now we did it in an open cup or an open beaker in the lab, and we didn't really collect, we sort of collected the hydrogen, but not really. But if we do this reaction in some kind of a container that has a lid on it, and you can see here that it's got a weight, so the lid is able to move up and down. So what's going to happen for two things? So when the zinc and the hydrochloric acid react, they give off heat. So they're showing you here the heat is leaving the system. But also, notice what happens. The gas forms and this piston moves up. So that is actually work that's being done. So the fact that we're pushing that piston up is a kind of work. So it's the equivalent of moving an object through a force field. So this is a type of work, pushing the piston up. It's sort of similar to, you know, like the pistons in your car. Gas is formed and the pistons move. And so that, again, is a kind of work. So in the case on that previous slide, there wasn't much happening. But what if that piston was attached to a crank of some kind? So you know, if you look at this system, so this is sort of similar to what you've got in your car. Gasoline burns and the piston moves when the work is done. If that's attached to a wheel, the wheel can do some movement, and you can see here that in this case, it's pulling a weight up. Anyway, the work can be done by this. That's why it's called work. So the reaction is causing work to the piston, which then can be used for other things. So in this case, the work is done by the system on the surroundings, and so work is considered negative. In another example, here, if you've got a weight on the sort of the plunger, I guess you could say, as the weight falls and the plunger comes down, it's actually work being done on the system. And so in this case, work is positive because it's being done on the system. In this case, the work is being released from the system and given out of the system. So that's why it's negative. Okay, we're just kind of restate the first law of thermodynamics, which basically says energy cannot be created or destroyed. Another way of saying it is we can say that the change in internal energy of a system equals heat plus work. So again, this is just a different example. Let's say we have a gas inside a piston and we heat it up, so heat is going into the system. What happens? The gas is going to expand, because if we heat it up, the volume should get bigger if pressure stays constant, which means we're not adding any more weight to this. But then as that lifts, work is done by the system. So if we add up the heat and the work, in this case, the heat is increasing, so we're adding heat to the system, so that's why Q is positive. Because work is being done by the system on the surrounding, it's pushing that up. The system has lost energy due to work, so work is negative. And so, but actually the change in overall energy has to do with both the heat energy and the work energy, whether it's lost or gained or either way. So in general, a system may involve work as well as heat, depending on the conditions. So notice that in all those conditions when we were dealing with gas, they had a lid on it. But more importantly, they happened at constant pressure. So if we talk about a reaction that takes place in an open vessel, we consider that constant pressure, the pressure of the atmosphere. And of course, that's most of the reactions, most of the things that we're going to be studying are open to the system, open to the atmosphere. So if we have heat, in that case, we call that Q sub P. And since pressure is constant, that's why we named this Q sub P, meaning heat at constant pressure. So at constant pressure, the only kind of work that is allowed is this pressure volume work, like we just saw with the pistons going up or down. So work that just changes the pressure and the volume, or either gotten from pressure volume changes or allowed due to pressure volume changes. So if we look at that, so work is only equal to P delta V, and it's negative because the work is being done it's going up, so it's going outside of the system. So yeah, the negative sign comes from the convention that W is defined from the perspective of the system. So if delta V is positive, that's meaning it's getting bigger. That means that work is doing the work is being done on the surroundings by the system, and so that's why it's negative. It's losing energy. Now, just by the way, some of this derivation here is not specifically going to be on the test in terms of you having to recreate it. We're just kind of working through it to come to our final results. So this is not something you have to recreate. Before we move on, let's define something. What is a state function? So a few of the things that we're going to be talking about, or we have been talking about, are called our state functions. So internal energy is an example of a state function. And what is a state function? It's the value of a state function depends only on the state of that on the state that a system is in, and not on how it was reached. So another example is elevation. Altitude or elevation is also a state function. So in other words, if I'm up here on the top of the summit I'm at a particular elevation. Let's say I'm standing on the top of Mount Kilimanjaro, then I'm at an altitude of 5,895 meters. It doesn't matter if I hiked straight up the mountain, if I took, this curly Q path, if I went round and round and round and round, or even if a helicopter came and dropped me off at the summit. So in other words, the path is not important, but just the beginning and the end. So we start at the base, we end up at the summit. What is my elevation? That's what a state function is. So internal energy is also a state function. It doesn't matter if you do this reaction in 3 steps or 1 step or 5 steps. The change in energy is going to be the only dependent on the initial state and the final state and how that changes. So now we're going to define a new value called enthalpy. So because we're talking about this, talking about reactions when pressure is constant. So we're not worrying about any kind of pressure or changes in pressure. So when this reaction occurs at a constant external pressure, in other words, an open beaker, just regular old reaction, then the heat of the reaction, which we sometimes called QP, the heat of the reaction at constant pressure, actually equals this new thermodynamic quantity that we're going to call enthalpy. And I think it's really came about because of this. So it's sort of like we're defining H, enthalpy, as the heat at constant pressure. So enthalpy is given the symbol H. Enthalpy is an extensive property because, as we said before, it depends on amount. So, if you react 1 gram of something, it'll have a particular enthalpy. If you react 50,000 grams, it's going to have a completely different enthalpy because it'll all be related to how much you have. It's also a state function, like we just talked about, because it only depends on the present state and the initial state, and is independent of the pathway that happened to get there. So the enthalpy, then, we're defining it as the change in enthalpy is defined as the internal energy change, and because we're only at constant pressure, any P delta V work that we have. And again, this is kind of a derivation that we're just kind of going to go with it. Since we know delta U equals heat plus work, and we know at constant pressure, Q is Q sub P, and work is minus P delta V. So if you plug that all into this equation, plug that into the initial equation. So if delta H equals QP minus P delta V plus P delta V, everything cancels out except the QP. So this is kind of the reasoning behind where this came from, but it's kind of like we're defining Q sub P as delta H. So we're going to kind of, they're kind of interchangeable. If we talk about the heat of a reaction at constant pressure, we're also meaning delta H, or the change in enthalpy. So the change in enthalpy is equal to the heat of the reaction at constant pressure. It's a better method of keeping track of things rather than the total energy, delta U. It's just easier to relate to and easier to keep track of. So we're going to be using this delta H to represent our heat of reaction. Okay, so delta H is essentially the heat obtained or absorbed, absorbed or actually released, the heat released or absorbed by a reaction in an open vessel where we're not really worried about the work portion. We're not measuring it. So it's easier to calculate. It's more useful than delta U. We don't have to worry about all that pressure volume work. And so we're going to use delta H from now on. Okay, so delta H, just like any delta value, delta always just means change in. So the change in delta H, or the change in H, will always be the H, the enthalpy of the final set of conditions minus the H of the initial. Since we're talking about a reaction in general, then final is where we are at the products, the enthalpy of the products, and the initial is the enthalpy of the reactant. So we can define delta H as the enthalpy of the products minus the enthalpy of the reactants. Now, we're going to apply it to our reactions. So when we see a reaction, so this is just nitrogen plus 3 hydrogen gives us 2 ammonia. Often now we will see a delta H next to it. So this is telling us what is the change in enthalpy for this reaction, or what, in other words, what is the heat of this reaction. In this case, it's negative 91.8 kilojoules. So a couple of things, because it's negative, it tells me that it's exothermic. If it's exothermic, that means heat is a product. Okay, if delta H was positive, that would mean endothermic, and that would mean heat was a reactant. But in this case, heat is a product. So a thermochemical equation is just the chemical equation for the reaction. We're going to include phase labels, and then we are going to have the delta H given to us right after the equation. Every once in a while, you might see it written in the equation, like for example, N2 plus 3H2 gives me 2NH3 plus 91.8 kilojoules. So if you see it within the body of the equation, notice that because it's a product means it's negative. So even though it's plus, it means because it's on the product side, it is delta H is negative, meaning heat is being released. So product released. And now we can add one more layer to our balanced chemical equation. So I can say 1 mole of nitrogen reacts with 3 moles of hydrogen to give us 2 moles of ammonia, and will give us 91.8 kilojoules of heat given off. So this is just a new layer. So if we have our coefficients, we know that 1 mole of nitrogen always reacts with 3 moles of hydrogen. 3 moles of hydrogen are required to give me 2 moles of NH3, and now we know also that to react 1 mole of nitrogen with 3 moles of hydrogen, we are given off 91.8 kilojoules of heat. So it's just another layer in our equations. All right, so let's talk a little bit about how we use thermochemical equations and what are some conventions that might be important to keep in mind. So first of all, if we change it, because it's a state function, and also because it's extensive property, if we change the equation in some way, we have to change the enthalpy, or the delta H. It will also change. So so keep these things in mind. First of all, it depends on the direction of the reaction. So we've talked about this kind of before. You know, if a chemical equation is reversed, then the value of delta H is also reversed. The sign is reversed. So, you know, if delta H is less than 0, it's an exothermic reaction. If you reverse the equation, the delta H will become positive because it's an endothermic reaction. So here's an example. H2 gas plus 1/2 O2 gas to form H2O liquid has a delta H of negative 286 kilojoules. So if we want to take the water and break it down to hydrogen gas and oxygen gas, then the delta H becomes positive. So it's just the sign changes, the value stays the same. Number 2, because it is extensive, it depends on the amount of reactants. So if you multiply an equation by any factor, then you also have to multiply the value of delta H by that same factor. So to find the delta H for the new reaction. So here's an example. For example, you know, we just looked at this, H2 plus 1/2 O2 to give us H2O liquid. Delta H is negative 286 kilojoules. What if we doubled that? So 2H2 plus O2 to give us 2H2O. Then the delta H would be negative 572 kilojoules. So we multiplied that by 2. What if instead we want to take half again? So half of H2 plus a quarter of O2 to give us a half of H2O. Well, we would multiply the original delta H by a half to give us negative 143. Finally, it's important to make sure you're paying attention to the phase. So delta H will depend on the state of the reactants and products. So often, especially with water, it's important to note the phase labels. So see here, if you take 2H2 plus O2 to make 2H2O in the gas phase, of course it's negative 483.7 kilojoules. If we're forming a liquid gas, it's actually more. Of course, what's the difference? The difference is the delta H of the condensation of the gas to the liquid. So make sure, we'll see when we start working with these, you have to look up some of the numbers, and so you want to make sure you know if they're gas or liquid. Let's just talk about some reactions that we know. What is the sign of the enthalpy in the following situations under constant pressure? So what do you think the sign, or in other words, is ice cube melting endothermic or exothermic? This one often confuses students. Remember, what do you have to do to melt an ice cube? You need to put heat into it, and so delta H will be positive. Ice has to absorb the heat from the surroundings. Q is positive, so delta H is positive. So it's endothermic. So what about 1 gram of butane being combusted to CO2 and H2O? Of course, the combustion gives off heat. We know that. So Q is negative, delta H is negative. That's an exothermic reaction. So like we've just been talking about, the quantity of heat will depend on the amounts of the reactants. And so what we do is we have a balanced chemical equation, and we can relate amounts of reactants and products, stoichiometry, like we've just been doing, but we can also relate it to the heat of the reaction. So the heat of reaction will be proportional to the amount of each reaction and product. So for example, let's consider this reaction that we just looked at. 2H2 plus O2 gives us 2H2O. So consider the reaction of hydrogen burning in the presence of oxygen at constant pressure. Given the following equation, how much heat would be obtained or be given off by the combustion of 5 grams of H2? So what we do know here is that 2 moles of hydrogen reacting fully will give us negative 571.7 kilojoules. But now the question is, how many grams? How much heat will be given off if we react 5 grams? So we just have to do a few conversions. First of all, we have to figure out how many moles 5 grams of H2 is, and then we know, just like we had before, that for every 2 moles of hydrogen gives off negative 571.7 kilojoules. So it's just an additional layer to our stoichiometry. 2 moles of H2 will always react with 1 mole of O2. 2 moles of H2 will always produce 2 moles of H2O liquid, but also now 2 moles of H2 will give off negative 571.7 kilojoules of heat. So what we have to do is we have to convert first from grams to moles. So if we convert 5 grams of hydrogen to moles of hydrogen, then we can use our conversion factor from the balanced equation. So we know that this is true. This is the conversion factor. And so 5 grams of H2, we first convert it to moles of H2. And then 2 moles of H2 gives us off 571.7 kilojoules of heat. So altogether, this reaction will give off negative 711 kilojoules if we burn, or if we react 5 grams of H2. And I guess it kind of think through it. 5 grams of H2, if each mole is 2 grams, this is about 2.5 moles, so it makes sense. Or 1.5 mole. 5 divided by 2 is anyway, yeah, 2.5, but then for every 2 moles, so it's a little bit more than 2 moles. 2.5 moles is a little bit more, so negative 711 is a little bit more than that. Anyway, hope that makes sense. All right, so let's look at one more example. Let's say we take a gummy bear which has 2.67 grams of sucrose, and we react it with potassium chlorate, KClO3, and so when 2.67 grams of sucrose react with 7.19 grams of potassium chlorate, 43.7 kilojoules of heat is released. So the delta H for 2.67 grams of sucrose reacting with 7.19 grams of potassium chlorate. Now, so here's the reaction. C12H22O11 plus, we had to balance it, 8 KClO3 gives us 12 CO2 plus 11 H2O and 8 KCl. Okay, that's the reaction of the burning gummy bear. So the question is, so if 2.67 grams of sucrose react with 7.19 grams of potassium chlorate, this much heat is given off. But what we want to know is what is the enthalpy for this whole reaction of 1 mole of sucrose? Okay, so first of all, this one's a little bit of a convoluted problem. The first thing we probably want to find out is, since we're given both reactants, we need to find out which is the limiting reactant. So 2.67 grams of sucrose is 0.00780 moles of sucrose. And let's just pick, I just picked CO2 as my product. So if I can make 12 moles of CO2 for every 1 mole of sucrose, then I can produce if I have 2.67 grams of sucrose, it'll produce 0.0936 moles of CO2. If I react 7.19 grams of KClO3, that is equivalent, using our mole-to-mole ratio, that's equivalent to 0.0880 moles of CO2. So which is our limiting reactant? The KClO3. Okay. So now what? All right, so we know that if we burn or if we react 7.1, that's probably it's aqueous, so it's reacting, 7.19 grams of KClO3, we get off 43.7 kilojoules. So 7.19 grams of KClO3 gives me 43.7. So again, what are we trying to find? We're trying to find the delta H for this reaction. What we know is the delta H for 7.19 grams of KClO3. So we're trying to find out what is it for this overall reaction. All right, since KClO3 is the limiting reactant, we can find out the delta H overall for 1 mole of KClO3. So if what I didn't show you was, what was it, 7.19 grams. Oh, that was on the previous page. 7.19 grams is 0.0587 moles of KClO3. So 43.7 kilojoules is given off for every 0.587 moles. So what does that mean? That means negative 744 kilojoule is given off for every 1 mole of KClO3. And if you go back and look at the reaction, we know that 1 mole of sucrose reacts with 8 moles of KClO3. And so the overall reaction, we have to multiply this by 8. Oops, sorry. Get my eraser out so I can erase that. So the enthalpy for the whole reaction is negative 5,960 kilojoules will be given off for every 1 mole of sucrose, 8 moles of KClO3.